So I ended up having to break this video into two parts. The first part, it was getting kind of long, running about 45 minutes, so I decided I'd break it up. The first part we dealt with the cal attenuator and we completed the IF adjustments. So we've done the cal attenuator error section, and we did that, and we adjusted the log and linear amplifier sections, and we did the third converter and second IF bandpass. So we did those sections there. So those are really the hardware sections of this service guide. So the next sections we're going to deal with are going to be for the frequency correction constants. So the first thing we're going to do is we're going to get section 10, which is the cal YTF. That's a routine that we'll run on the analyzer. Then what I'm going to do is going to perform the frequency response section 16 here for the first band, the low band on the spectrum analyzer. So like I mentioned earlier, we're dealing with an 8595E spectrum analyzer, which has two bands, and I'm going to do the low band, which is band 0, and that's going to go from the bottom to 2.9 gigahertz. And then after we get frequency correction constants for band 0, then I'm going to go back and perform the cal mixer adjustment routine, which if you look at this section here, the cal mixer, it optimizes the DC bias of the dual band mixer when in the high bands. And one thing to note here too is that when you run this routine, you will need to make new frequency response correction constants. So they must be developed following the cal mixer adjustment routine. So reading through this, it seemed to make sense that if we do the low band first, that's not going to be affected by the cal mixer. It looks like the cal mixer primarily is going to affect the higher bands. So we'll do the low band first, then run the cal mixer adjustment routine. And then once we complete that, then we will go back to the section 16 here, and we will do the frequency correction constants for band 1, which is going to be the 2.9 to 6.5 gigahertz, so the upper band of this spectrum analyzer. So for doing the frequency response, first thing I'm going to do is the band 0. I'm going to use this Agilent, this is a 8648C, so this unit goes up to 3.2 gigahertz, so that'll cover the range that we need. And I've got it set up for the correct frequency steps, so we're looking at a frequency step of 72 megahertz as we increment the frequency up, and of course starting at 12 megahertz with the amplitude set for a reading on the spectrum analyzer. And I've got so here's my setup right now. I've got the spectrum analyzer already set up per the procedure, and I'm feeding the signal in from this cable to a power splitter, and on one side we're going into the spectrum analyzer, the other side we're going to a power sensor, and that's going up to my power meter up there on the rack. Off the power splitter we have two very close points of reference here for the spectrum analyzer and the power sensor, and this power sensor's matched pretty well for the split power, so it's sending power equally to both ports. Now, one thing that the service manual does talk about, because here's the setup here, they're using a measuring receiver, which I don't have a measuring receiver, but I believe the measuring receiver is essentially an RF power meter and power sensor all in one unit here. I'm having to use some alternative measurement methods to perform this, but I think it works out pretty well. So you see how we got the equipment set up, and that's similar to the way we've got our equipment set up now. And now one thing, so after we go and we set up our signal generator, and we'll set up the spectrum analyzer and lock it to, so we turn corrections off and we lock it to band 0, which is the 0 to 2.9 gigahertz. And then we'll set up the analyzer. So what this will do is this sets our our reference point here. So we're referring all of the frequency measurements to a frequency of 300 megahertz. So all the corrections will be based off of our reference reading, which we take at 300 megahertz, and then the corrections will be corrected back to that value there. So once we set our analyzer and our signal source up, we'll adjust the signal source for a power level marker track amplitude reading of -9 plus or minus 0.1 dB, and we should be at when you perform this step here, you'll be at 300 megahertz. So I'll go ahead and set that up now. So we'll put this up to 300 megahertz, and we'll put our frequency at 300 megahertz there, and then we'll adjust the signal source down for our so now we're sitting at 300 megahertz, and we've adjusted our synthesizer to a marker track reading of -9 dBm. And what you'll do is it tells you to press the ratio on the measuring receiver, and what that does is that takes a ratio reading, which will ratio the current reading that you have to all additional readings that you take. So it basically sets the analyzer at a reference level. Now, on my power meter, if I want to do a ratio, I have to use two power sensors because it's a dual port meter. But what we can do is we can take a relative reading, and that's what I've got here. So we go out of relative mode, we see that that is our current power reading off of our power splitter here. So we're at our 300 megahertz reference signal level, and we're seeing a power level there. Now when I hit the relative button, that'll go to 0, and so now all of the readings that we take will be relative to that initial power reading at 300 megahertz. And what we'll see now is as we change the frequency here, and we adjust the frequency the power level going into our spectrum analyzer for a -9 dBm marker track reading here, then we can take the relative signal on the power meter up there. So we're looking at 0 right now, so I'll go ahead and take the first reading. So I'm going to put the signal generator down to 12 megahertz, and we'll put the spectrum analyzer at 12 megahertz. All right, and then we'll adjust our signal source for a marker track reading of 9 dBm, which is what we have there. And we see, so we got 9 minus 9 dBm, and you see now we've got our relative power meter reading of minus 0.8 dBm. As we change the frequency going into the spectrum analyzer, we'll have to update the power meter with the correction factors for the calibration factors for the power sensor. And I've already got it set to so for 10 megahertz here, because I'm using this this is an 8482A power sensor, so this is a lower frequency up to 4.2 gigahertz max frequency. This is an 8481, I believe, power sensor. And as you can see, it goes to 18 gigahertz, but it doesn't. It really doesn't have very detailed correction factors below 3 gigahertz, and that's really where we're wanting to measure here. So that's why I chose to use the 8482 as opposed to the 8481, just to get the more resolution at the lower end of our frequency range there. But anyway, so we complete take our relative reading, we'll record that, and then go on to the next one. Each time incrementing the signal generator source up 72 megahertz and incrementing the spectrum analyzer up 72 megahertz. And it has you set the step up. So you see the step is 72 megahertz. So every time you press the up arrow key, it'll increment that 72. Once we get the spectrum analyzer and the signal generator on the same frequency, adjust the amplitude for a -9 plus or minus 0.1 dBm marker track reading. And then once we've got that adjusted, then take a relative power reading on the power meter and then record that on the data sheet. And we move on to the next one. So we'll move all the way through all of these frequencies up to the top of the band, which is a 2.892 gigahertz. So as you can see, I've already completed that, and these are the numbers I've recorded here. Did get some up at the higher end of the band. We did get some pretty large values here. Is plus 4.82. There's a 5.02 there. So we did get some large numbers, but you know, it kind of comes and goes here. They get bigger and smaller, so sort of fluctuating back and forth there as we go. Of course, at 300 megahertz, we had 0 because that's where all of these values are referenced to at 300 megahertz. So we would expect to have 0 at 300 megahertz. So we completed our cal YTF, and we're going to hit the store cal. All right, and then after we get that completed, we'll need to do the cal mixer adjustment setup. So we'll hit the analyzer preset. All right, and then we're gonna unlock the we're gonna put in the passcode. This is gonna unlock the unit so that we can make changes to our calibration data. All right, so now we've put in the passcode there. We'll go to cal 1, 2, or more, and then we're gonna go to service cal, and we'll do cal mixer. All right, and so the cal mixture is complete. Looks like our optimum bias number is 1434. So we'll write that down. That way, in case we need to put that in, we can. And what the step procedure is going to have us do now is, what it says is the cal done will be displayed, optimum bias, and we'll press the store cal. All right, so there we go. We'll hit cal stored. All right, so let's go ahead and take a look at that information here. And display cal data, and there we see that our new mixer bias 1434 is stored in the instrument. So that will store the data to the mixer. And we can also see here too, here's our cal attenuator error constants that we came up with in the last video there. So the next thing we're going to do, now that we've completed the cal mixer adjustment, is going to perform the frequency response for band 1. So we'll set the equipment up and then we'll take a look at the setup for performing that test. We're getting into the band 1 correction factors, generating the band 1 correction factors, and pardon the fan noise, but I got a lot of different equipment running here, and we'll get into that in a minute. So first thing we're going to do is jump back into the section here before we did the band 0 adjustment, and we'll set up our spectrum analyzer for the 300 megahertz, basically our base measurement for taking our relative readings. And I've done that already, and I've got the equipment hooked up here, so you see that I'm feeding in the 300 megahertz source here through this power splitter, going to a power sensor here using the 8481 power sensor now this time. And we got our power meter set up here, and we're going to take our relative, so we're going to put this in relative mode here. And the first thing we have to do is adjust our signal source. After we get the spectrum analyzer set up, we're on peak and our marker, and we're looking for a -9 plus or minus 0.1 dBm reading on our marker track reading, and that's what we have set up here. So I'm going to hit the relative button on our power meter. That's going to go to 0. So now all of the readings that we take from this point on are going to be referenced to that 300 megahertz reading there that we had, that we took the relative from. Using this sweep generator, this is an 8620C sweep oscillator, and with the 86290B RF plug-in module, we're using the 2 to 6.2 gigahertz. We'll actually use 2 ranges of this. We'll use this range, and then for the very top of the range, we'll switch over to the next band up, which I believe is a 6 to 12 gigahertz range there. And I've got my signal coming out here, going into our RF power splitter, and we're monitoring our power level here with the 8481 power sensor. And I've already made the first adjustment here, so we're starting at 2.75 gigahertz, so I'm going to use the 3 gigahertz correction factor, and then I'll adjust those as we go up the band there. Monitoring the frequency here on this microwave frequency counter. As you can see, we're set to 2.75 gigahertz, and I've got this coming off of the rear of the instrument. I can't take a reading off of the RF out. I've tried splitting this signal out, and it makes it lowers the signal power level too low to be able to perform this test. So I'm using the aux out jack on the back here. Now the aux out only spans from 2 to 6.2 gigahertz. So when we use the next band up, this frequency reading here will be half of the actual frequency on the RF output here. So we'll have to multiply this by 2 to get the actual frequency. And we're set up, as you can see here, we're in CW, and I'm using the CW and the CW vernier here to get our frequency adjustment. Just as a precautionary measure, I've got a 10 ohm attenuator in line here to give me extra assurance that I'm not going to violate the 7 dBm output here. So between the cable loss and this 10 dBm attenuator, we won't have to worry about damaging the sampler. As you know, and I talked about this on the video when I did this frequency counter, these samplers can be damaged very easily by overpower, and that 7 dBm max power input is pretty low power input there. So just keep that in mind if you're going to use one of these frequency counters. So we took a look at the setup, and I'm going to go ahead and perform the first measurement here on the screen here, and so we'll walk through how this is going to work. So first thing we'll do is press the peak search, and we'll get a peak on our spectrum analyzer there. Then we'll make sure that the marker function is set to marker track on, because we want to track that peak. Now for the band 1, what is going to have us do is something different than when we did the band 0. So we're going to press amplitude, and then we're going to do the pre-select peak function there, and that's going to peak our signal coming into the analyzer. Once that is complete, now we will perform the power level adjustment. So I'll adjust the power level on the signal generator here, and remember we're looking for a power level of 9 plus or minus 0.1 dBm. So I'm able to get pretty nice fine control here on this signal generator there. So we see that we've got our power level there of minus 9.03 dBm. All right, and so once we've completed that measurement, we're going to look up on our power meter, and we see that our relative reading is plus 4.46. So that is our correction factor, and we'll write that down on the chart. And we've recorded our correction factor there on the chart, and next thing we'll do is we'll step the synthesizer up to the next step. So the steps for this band are 234.9 megahertz steps. So because I'm not using a real sweeper, or I'm not using a synthesized sweeper, I've got to make the adjustments manually with the CW control on this one. So I have to do a little bit of math here to figure out where the next frequency range is, and I'll get that figured out, and then we'll look at the data once I complete the readings. But on the spectrum analyzer, it's easy. It has you set this up ahead of time, so you'll hit frequency, and you can see that we've got a step already programmed in of 234.9 megahertz. And the way that you'll do that is just by pressing the this arrow key, arrow button right here. You'll step up the next frequency band. So one thing I noted too about this service manual is, you know, for HP service manuals, this one seems to have quite a few errors in it, and one that I've noticed here on this the frequency response correction constants here is they didn't include a table for band 1. So if you look at the tables here, so this is page 116. So page 115 was the band 0, and they go straight into this is continuing from band 0 here. So 1.596 gigahertz, and then where they start is band 1. They start at 6.1 gigahertz, so that looks like that should probably be band 2, and they keep on going with band 1 there labeled as band 2, and then they repeat here at band 2. They start again at 6.1 gigahertz. So it looks like what they should have done when they put this chart in was they should have said band 1 and started at 2.75 gigahertz and counted up, but they did not. So I'm just going to pencil in the numbers here on this chart and write them here for the frequency, for the different frequency breakpoints here, and we'll get the correction constants restored written down on this column here, just like we would if we had to chart it'll just take a little more work on my part. So we'll look at that here in a minute once I complete this first run of data for the band 1 frequency correction. Completed the first round of measurements here using this sweep generator, and as I mentioned before, for the last two measurements here on the band 1, I had to use the 6 to 12 gigahertz range for this sweep generator there to get up to the final readings at 6.275 and 6.50 gigahertz. And as we can see here, I've still got the measurement up on the spectrum analyzer showing there, and on the frequency counter. And as I mentioned before, so the actual frequency of the output of the generator is double this, so 3.25, so double that is 6.5 gigahertz. And that's because we're using the to monitor the frequency of the signal generator using the aux out on the back, which is the base frequency of the generator before it goes through any multiplication stages. So there you go. So for those last two measurements, we'll have to use this times 2 to get the actual frequency. And you can see here showing our relative measurement 3.52. I actually recorded on the paper here 3.47, and it sort of fluctuates around there. You can see it's dropped off just a little bit and come back up, and I think that's due to this generator is probably not the flattest source, so it tends to fluctuate a little bit. So when I take these readings here, I had to sort of watch the power meter a little bit and see where the fluctuation was, and kind of take a sort of a middle value of that fluctuation range, and that's what I have here on the sheet. And like I said, just reusing this column here for the band 0, because they didn't give us a correct band 1 table. Also too, these are the correction constants, or the correction factors applied to the power sensor as we moved up the frequency range there, applying those corrections from for the power sensor here, and that's on the chart there. So next thing I'm going to do is I'm going to set up or rather I'm going to set up a different setup, and we'll take this measurement again, because just like I did with band 0, I took I think I ended up taking 3 sets of data to get the corrections to see, because if this is being done correctly, it should be somewhat repeatable with the results there. So I'm going to, but in this case, I'm going to use a different instrument, a different signal source, and we'll see if we get any different results than what we've got here on for this set of data. All right, so I've got the new setup now, and I'm going to explain here what we've got. So I've already gone ahead and done the made the baseline measurement of 300 megahertz, and I've got the analyzer set up for the first reading at 2.75 gigahertz. And here is our new signal source. So we're going to use, this is an HP 8672A, and it goes from 2 to 18 gigahertz, and right now I've got it set for the first reading of 2.75 gigahertz. And this one has the option where the RF port's on the back, so I'm feeding the RF from the signal generator out of the rear port into a coupler. This is actually the coupler that I removed from this spectrum analyzer when I upgraded to the tracking generator option. So it's a directional coupler. It's good from 2 to 8.6 gigahertz, so it'll work for the frequency range here that we're testing. We're going from 2.75 to 6.5 gigahertz. And off the couple port, I've got a 20 dB attenuator out to this coax here, which is going to the frequency counter there. Just to the so the coupled port is a minus 16 dB plus an additional 20 dB of attenuation to ensure that I don't damage the input to my microwave frequency counter there. And anyway, from there, from the coupler, it's going to go into a power splitter. We've got the the HP 8481 power sensor setup here on the output of this port, and the other port going to the spectrum analyzer. And we're taking the relative power reading here for our first measurement. See, we're getting a 4.3 dB relative measurement there. So I'm going to complete or repeat this section here, taking the new measurements from the frequencies specified here, and going to write the new measurements down here, and then when I get done, we'll compare the differences and see if there's any significant difference between making the measurements with the two different signal sources. And we'll look at the results here in a minute when I get this this next run of data complete. All right, so finishing up, take the last reading here at 66.5 gigahertz, and we'll look at the results now on the chart here. All right, so as we can see, the numbers are pretty close, but they all this second column here is the results that I got with the 8672A synthesizer, and they're a little bit lower. They're all a little bit lower than the ones that I took with the 8620C with the 2.82 to 18 gigahertz plug-in module. And I think I'm going to use the second results just because I have a little more confidence in the 8672A, mostly because what I observed was with the 8620, I had to sort of get a median value here as the power level, the relative power level fluctuated somewhat. So what I would do is I would look at the low and the high and sort of take a value in the middle. With the 8672A, I didn't really see it at all. Once I got the power level adjusted, the difference or the relative power level was pretty stable. It wasn't a whole lot of going back and forth. So I feel like I have a little more confidence in the second numbers, and so those are the ones I'm going to use to put in for the correction factors. So we've got correction factors for band 0, and now we've got new correction factors for band 1. So the next thing we'll do is go and put those into the instrument. So I've compiled all the data. I took the 3 passes that I took on band 0, looked at all the data, averaged them out, and I'm going to use the average of the 3 runs for the data on band 0. And on the band 1, I'm going to use the second run of data that I gathered on using the HP 8672A synthesized signal generator. I think that one was more accurate. So we're going to enter the flatness correction data once we've gotten this data that we've collected here. So I've already gone and put the instrument back in preset. So we're going to enter the passcode for making changes to the correction parameters. All right, then we'll access the data. We'll press the cal button, and we'll have to go 2 pages over service cal and flatness data. So right now we have no flatness data in the spectrum analyzer. This next step here, there's a caution here in the manual that says the next step will erase all the current flatness correction. And I mentioned that earlier in the video that when we initialize the flatness area, it's going to erase the data that's already there. So if you're doing this and you already have correction data in, it might be a good idea to back that up in case you need to revert back to that previously stored data. Since I don't have any data in mine, it won't be an issue here. But the first thing we're going to do is initialize the area of the memory where the flatness correction data is stored, and that is going to be by depressing the INIT flatness. And then we will press preset. All right, and then once we do that, we'll put the passcode in again. And we'll go over to cal, one or more, two or more, and service cal, and flatness data. All right, and then we'll enter the flatness corrections. We'll press the edit flatness. And so we're starting with the first step. And the way we'll enter the data is you'll key the data in using the numeric key, and then you're going to terminate with either a minus dB or a plus dB, depending on what your measurements were. And then you'll scroll through the data for each data point using the up key. You can scroll back and using the down key and make changes or whatnot. So I'm going to put the data in, and then when I get ready, when I get all the data put in, we'll pick up the video from there. All right, so all of the flatness data has been entered. So once all the flatness data has been entered, we'll press the store flatness key. And we get a message saying flatness stored, and we'll press more, and we'll press exit. All right, so there is our spectrum with the flatness data, and that looks more like the noise floor I was used to. So I looked back on some of my one of my older videos on the spectrum analyzer to look at the noise floor, and that looks more representative of what that floor should look like. So if we go to cal, over to service cal, and we can retrieve our flatness data. We can have a look at it there, and we see that our flatness data is shown there after we updated the flatness data. And it looks like we can scroll through the span here and look at the various points. So if you're interested in backing up your cal data, this is how you would do it. You just have to scroll through on these points and record your values there for your offsets. And then that's it, because we just have the two bands, so it'll end at 6.5 gigahertz. All right, so next thing I'm going to do is I'm going to go ahead and take a look at the calibration manual, and I'll probably run the checks in the calibration manual and fill out the test card, and then we'll take a look at the cal card once I get those sections complete. So completed the all the portions that I could of the calibration manual. Most of the sections I was able to perform with the equipment I had. There were a couple of sections that I wasn't able to perform just because I don't have the equipment. And so we'll look at that real quickly here on the test card. And we'll focus on the measurements that we actually made changes to. Here's the frequency readout accuracy marker and the marker count accuracy here. No issues. Measured noise sidebands and system-related sidebands, no issues there. Frequency span readout, no residual FM, sweep time accuracies, and scale fidelity. Those have no issues as well. And of course, some of these sections were not performed because a lot of these are applicable for option 130. Reference level accuracy completed. Amplitude, absolute amplitude, calibration and resolution band switching uncertainties here. Frequency response. This was one of the ones that is affected by the frequency response routine, where we had to create new frequency correction constants. And again, so with what we did to create those new constants, the unit was able to pass within calibration here. We see our max positive measure was 0.073, and the max allowed is 1.5, so well within the limit there. And our max negative response here was a minus 0.54, and our max allowed is minus 1.5. So that was good there. That was for band 0. And for band 1, again, our max positive response allowed was 2 and measured a 0.41. And our max negative response allowed is a minus 2, and I measured a minus 0.58. And peak-to-peak response allowed is 3, and I measured a 0.99. So no issues there. No other spurious responses noted. Measured gain compression. The gain compression was one of the measurements I wasn't able to perform exactly as directed, because I don't have two signal sources that will go above that will go to 4 gigahertz. I tried using the the HP 8620C, the sweeper unit, and it was just the frequency was too unstable to get a meaningful reading. So what I ended up doing was doing the same measurement at for the greater than 2.9 gigahertz. I took it to 3.2 gigahertz because I could use the that 8646C, and I could use the 8672A. Those two units, the 8646C with a maximum frequency of 3.2 gigahertz. So I was able to perform that measurement at a slightly lower. I think the test wanted to do it at 4 gigahertz. So was able to measure both bands there with a little modification. No noise issues, no residual responses. I did the fast time domain sweeps measurement because my unit is included with option 101. Again, some more. Now we're getting into the tracking generator. So when I got into the tracking generator, here's where I started noticing some problems. And I kind of knew that I would probably not be able to complete this section because, as you saw in the previous video, the tracking generator in this unit is not very flat. And what I learned was it's not very flat at all. And I guess that's kind of what I get for buying a used tracking generator that who knows where it came from. But anyway, that's what we got. So the amplitude accuracy was fine, no issues there. The power sweep just slightly under at 8.95 dB. The spec was 9 dB. I will accept that for now. I might try to go back and make some adjustments, see if I can get that, but it's pretty close to where it needs to be. Now the level flatness, which is what I expected, I was not going to meet, and it didn't come anywhere close. So from 9 kilohertz to 100 kilohertz, that was fine. 0.18. The 100 kilohertz to 2.9 gigahertz, the maximum deviation measured was 3.82 dB, with the spec is 2 dB, so well over the limit there. And our minimum flatness, again, the maximum deviation on the minimum was 2.344 dB, so that was outside of the allowable minus 2 dB deviation. So my tracking generator is not very flat, unfortunately. One thing I was able to correct, though, is tracking generator feed through. So I took the measurements initially for tracking generator feed through, and I found that I had some feed through at 2.6 gigahertz and 2.9 gigahertz that were above the allowable feed through level of minus 112 dBm. So what I did was I ended up taking the tracking generator, the whole RF assembly out, and the problem was when I had originally put the modification in, I didn't use rigid coax, and so the coax that I did use, I guess was too leaky, and it was allowing some of that tracking generator signal to leak out in the instrument. When I replaced the coax with rigid coax, that cleared up the tracking generator feed through, and I ended up getting it back into allowable spec. The highest level was minus 115.7, with the max allowed was minus 112 dBm. So changing out the coax on that modification got that feed through problem resolved. And I may also look at, since I have the clips, I may dig into the control circuits and see if there's maybe some things I can check, some adjustments I can make, and if I get some more information there, that'll be something for another video, not for this one. And I think that's mostly it. Yep. So the rest of this is for the different options that I don't have. So big things to take away from doing the cal section is that all of the recreating the calibration constants for the frequency corrections and the attenuator cal error, all of those things that we did and made the changes to the instrument. Still, the spectrum analyzer is performing within the specifications of the cal record. Here's the units up and running here, sitting on the all of the test equipment I had to drag out to do the calibrations. I had to even drag out this 8640B signal generator here for taking some of the readings. The cal manual wanted this instrument to be used, so I got to pull that out of the closet and put it into service. And then, like I said, the 8646C, we saw that one, and then my new 8672A signal generator, which came in very handy for doing this calibration, for getting the nice level, stable signals that I needed, and for getting the frequency correction, recovering the frequency correction. So that's going to be it for this video. I hope you enjoyed this series on HP 8595E Spectrum Analyzer. It's back up and working. Some things I've got to work on still. I'm going to take a look at the tracking generator. If I get some information that might be useful, then we'll have a video on that later on. But that is going to complete this series of videos. I hope you found something useful or enjoyable. And as always, thanks for watching.